Welcome to Web Applications for Loom. My name is Mark Thomas. I'm a committer on the Apache Tomcat project. That's where I get to spend the majority of my time, although over the years I have sort of expanded my role and sort of dabbled a bit in projects that support Tomcat and also wider roles at the ASF. Back in the days of Java EE, I was on a handful of the expert groups, and that's transferred over to Jakarta, where I'm on the expert groups for the four main specifications, well, not expert groups, projects really, isn't it, at Jakarta? The four main projects that Tomcat implements, so that's Servlet, Pages, WebSocket, and Expression Language. My day job is as a staff engineer at VMware, where I have a very simple job description. And that is go and do whatever you think is best for Apache Tomcat. So I'm very fortunate I get to spend my time basically working on my hobby. So today we're going to talk a little bit about Project Loom. I've pulled the definition of Loom off their wiki. And the bit that I'm particularly interested in today is that bit in the middle, the easy to use, high throughput, lightweight concurrency. What does that actually mean for web applications? Well, in order to put that in context, I want to do a brief history, and don't worry, it will be brief, of servlet scalability. So we're going to go all the way back to the mid to late 90s and HTTP 1.1, and then look at the key changes that we've had over time so we can see where virtual threads fit into those changes. And to do that, I'm going to do it with this sort of example simple web application. So we've got a simple web application in the purple or pink box, depending on how your eyes see it. That's deployed on a Tomcat instance. That's on a JVM. Tomcat has a pool of threads. That's that pool there, each T representing a thread. And then underneath that, the OS is responsible for scheduling those threads on the 4 cores we've got available on this system. The web application is talking out to an external service. We'll see why that's important in a couple of slides' time. And we're really interested in 2 things on the left-hand side. Connections, which are active connections from clients to Tomcat that don't have a currently executing request on them, and actual requests where there's a request in progress. So back in the days of HTTP 1.0, life was really simple. Users connected, they sent the request, the response was generated, it got sent back, the connection was closed. Nice and easy. From working out what was going on, how many threads do I need? Well, you need 1 thread to process the connection, so that's your maximum number of connections. It's the same as the maximum number of concurrent requests, because you've got 1 thread per connection, 1 request per connection, and the maximum there is the thread pool size. So it's all nice and simple. So as you see here, we've got 5 incoming connections. We've allocated 5 threads from our thread pool to process those. Now, back then, well, still now actually, creating connections is expensive, and that's kind of why we've got Quick. But back then, they were even more expensive because it requires a network round trip in order to establish the connection. So that adds quite a lot of latency. So the solution is pretty simple. Well, we'll just add keep alive to the connection. So we keep the connection open. That saves the round trip. That's great. Now, HTTP 1.0 had some few issues with that around interoperability, particularly with proxies. But that all got fixed in HTTP 1.1. So we got our improved latency, which is great. Problem is our scalability actually got worse, because now we're still having to allocate threads to those connections, even when the connections aren't doing anything. So we end up handling less concurrent requests because the majority of the time the connections are idle. That can quite easily lead to thread starvation. And way back in time, the approach Tomcat took to this with its blocking I/O connector was a fairly simple but brutal one. Was, OK, first 75% of the thread pool, that's fine. We'll just use keep alive as the user's request. Once we're in the top 25% of the thread pool, doesn't matter what the user asks for, they are not getting keep alive. We'll process the request, we'll close the connection, and we'll release the thread ready to do the next one. And it was like that for a little while, but clearly there was scope for improvement. And that came along with non-blocking I/O. In Tomcat, that's the NIO and NIO2 connectors. I'm pretty sure the APR native connector did it as well. Now, it would be obviously, the more NIO we can use, the better. The problem Tomcat has at this stage, as do all servlet containers, is that the Servlet API only understands blocking. That only does blocking I/O, doesn't do anything else at this point. So the containers can use non-blocking I/O to a point, but once processing enters the servlet container, you're back to blocking, and we can't do anything about it. We have to wait for the the request and response to exit again. But we can make quite a big improvement. What we do now is when we receive a connection, that connection gets passed to the polar, and the polar can handle tens of thousands of threads. And when the polar detects that there's data, sorry, tens of thousands of connections rather, so when the polar detects that there's data on a connection, then it passes the connection to one of the request processing threads, and that's when the thread gets allocated. So in this way, we're only allocating threads to connections that actually have data that need processing. So now we're doing well again. We've still got our latency improvements of keep alive, but we've got much better scalability. Our maximum connections are a lot higher. The defaults in Tomcat were then, I think they still are now, about 10,000 connections and 200 threads in the thread pool, and that's quite comfortable for most web applications. So our maximum connections is much, much greater than the maximum number of concurrent requests, but that is still the same as the thread pool size. Now, the next step is that we eventually got non-blocking I/O in the Servlet asynchronous API. And what that lets us do is when the web application is doing something, normally calling an external service that's going to block, rather than keeping a thread allocated for that entire session, that entire blocking operation, what it does is, right, fine, we'll use the non-blocking API, and so we'll release the thread back to the thread pool so it can go do something useful, and when we get the data back from the service, that's when we'll reallocate a thread and carry on processing. So here you can see we've still got 3 threads in keep alive. The second one is obviously doing some sort of non-blocking operation to the external service, and the third one is actually doing some real processing on a request thread. So now we're at the point where our maximum connections is much, much bigger than our maximum concurrent requests, but that is also bigger than our thread pool size. So we've improved our scalability. And really, all of these changes, they're moving in that direction. It's largely improving the scalability of things. So where do virtual threads fit into this? Well, a brief summary of virtual threads. The pre-Java 21 threads, as we all know them, get referred to as platform threads, and virtual threads are this new cool thing. Well, not that new, as Jürgen was saying in the last session, but they're not always linked to an OS thread. They're purely within the JVM. They do have a stack, but rather than having a separate memory area for the stack, it's held within the heap. That has potential implications for GC. And they have their own scheduler. It is the JVM that is entirely responsible for deciding which of these 100,000 virtual threads I've got are actually going to get mapped to this small pool of platform threads, and which one's going to execute. And that's entirely under the control of the JVM. So the idea is that because they're so lightweight, if you've got something that needs to be done, you create a virtual thread, it processes the task, and then you just throw the virtual thread away. You're really not meant to be pooling these things. That's not how they're intended to be used. In terms of what actually does the work, as I said, the virtual thread scheduler has a small pool of platform threads that does the real work, and that's normally set up as one platform thread per processor core that's available on the machine. And then, as I say, it's the virtual thread scheduler that will attach a virtual thread to a platform thread, let it do some work, and at some point in the future, detach it. So there is one key difference for virtual threads, and that's when they come to blocking operations. And really, this is where the JVM does a little bit of magic for you. With a platform thread, if you come along to a blocking operation, well, the platform thread's just sat there. It's blocked. It has to wait for the blocking operation to complete. It's using up quite a lot of resources, and in fact, there's nothing you can do about it apart from hope that the blocking operation finishes soon. With virtual threads, something very different happens. When it gets to a blocking operation, it actually starts doing it non-blocking. The platform thread is detached. That's allowed to go back to the thread pool, and the scheduler can use it to do other useful work. When the non-blocking operation completes, that then allows the virtual thread to be available to the scheduler again, and it will continue when it's reattached to a platform thread. So essentially, you're getting non-blocking for free. It's really neat, and it can be incredibly powerful to help an application that's largely blocking. There are a couple of gotchas. Some of these are probably more relevant to Tomcat, but they might ring a few bells for you as well. Thread locals are an interesting one. Because a virtual thread is used for a task and then thrown away, if you're putting something in a thread local, that's going to get thrown away as well, or at least that thread's copy of it gets thrown away. So it then depends very much, what are you using that thread local for? Generally, it falls into two categories. If you're using it to pass context that you can't pass through some sort of API boundary that you need to get across it, that's fine. That's a perfectly reasonable use. Unfortunately, Tomcat is using a lot of the other use. Tomcat has quite a lot of fairly expensive objects that it needs to create or it needs to use in order to process a request. So rather than recreate a new one of those objects every single request, what it does, it creates it once, pops it into a thread, well, uses it, recycles it, pops it into a thread local, and then the next time that thread is processing a request, it just pops the object back out of the thread local, and it's a lot faster to do the recycle, put into a thread local, get out of the thread local, than it is to recreate a new or create a new object. The thing is, that doesn't really work with virtual threads, because you'll put it into the thread local and then it'll just get thrown away. So you won't be able to then go and retrieve it. So one of the things we'll be looking at in Tomcat is what alternative caching strategies we've got available. The other one is pinning. It's a problem at the moment, and it's on the list of things. I believe it's in the category of we're going to try and make this not the case, but it is the case at the moment, and that's try on a sort of OpenJDK end of things. If you have a virtual thread that's running on a platform thread, and that enters a synchronized block, the virtual thread is pinned to the platform thread until you exit the synchronized block. Now, if you're just using it to create a memory barrier, so it's a quick in and out, that's absolutely fine, no issues at all. If you're using it for a much longer operation, and particularly if there's blocking going on, then it is a problem. And this is another issue that Tomcat hit. One of the challenges we had when we were implementing the Servlet asynchronous API is that sometimes you can get a scenario where, and the Spring MVC team were great at finding these and creating bug reports for us. The web application would start an asynchronous operation, and whilst that main request thread was still processing, the asynchronous operation would actually finish, the callback would fire, and it would start being processed as well. And at this point, you'd have two threads both processing the same request and response. And generally, that's a disaster waiting to happen. It's normally a security vulnerability. We really don't like that. So we came up with a really simple solution. Fine, we'll just put the request processing in a synchronized block. If you haven't got the lock on the socket wrapper, you can't process the connection. Nice and simple, solved all the problems, but doesn't play nicely with Loom, because we've now put the whole request processing block in a synchronized block. Fortunately, it was a really easy fix. Just needed to switch it to reentrant lock, and that problem went away. I'd expect most cases, if you've got blocks like that, you'd be able to do the same things in your applications as well. So, what do virtual threads mean for our little diagram? Well, at some level, not really very much. Rather than the little T's processing the request, we've got little V's because they're virtual threads. Okay, we've added the virtual thread scheduler, and there's a smaller thread pool underneath. But from an application point of view, potentially nothing's changed at all, as long as you've avoided those couple of constraints. However, this does sort of create a whole bunch of different questions, some of which, emphasis on some, I'm going to try and cover this afternoon. So, what's the impact on throughput? What's the impact on scalability? What about GC? Memory footprint? Oh, and all of those are interrelated as well, just to add to the fun. Went to a great talk at Java 1 a few years ago on garbage collection, and the one thing I took away from it, or a couple of things I took away, but the one was, you can pick any two of high throughput, low GC latency, and small memory footprint. You can have any two you like, but it's going to be at the expense of the third. So they are going to be interrelated. We can't optimize for all of them. But really the question, well, what impact does Loom have on all of these? What impact does it have on the way they interact? These are not simple questions. And there's going to be an element of, well, it depends on the web application as well. So we can do so much, and I'll talk about what we've been able to do so far and what we're hoping to do in the future. But a lot of this is going to come down to really the only way you're going to know for sure is to run it on your web application. You can certainly get some ideas and get some indications of what you're probably going to see, but ultimately, if you want real figures, you're going to have to do it on your app. What's the impact of that extra scheduler? This, I think, is where it gets potentially really interesting, and it depends how you run your code. So imagine you're running for whatever reason, maybe it doesn't happen that often these days, but you never know. You've got your Tomcat server on a machine, and it's using platform threads, it's got its 200 platform OS threads. That's running quite heavily. There's some other process on there as well, and it's got, let's say, 50 platform threads. Now, the OS scheduler is going to somehow allocate CPU processing power between that Tomcat process with 200 platform threads and our other process with 50. I don't know how it's going to do it. It's going to vary via operating system, but however it does it, there will be an answer. Then we switch Tomcat to use virtual threads. Now what the OS sees, so let's assume we've still got these 4 cores because it makes it more extreme. I've got this Tomcat process that's got 4 platform threads, and I've got this other process over here that's still got 50. Now how does the OS allocate CPU across those platform threads? Is it going to be the same? Probably not. How different is it going to be? I don't know. But again, it's those sorts of things that you need to be aware of. How are other things that are running on that box going to interact? Oh, and chuck in 1 or 2 layers of virtualization and other schedulers as well, and it gets really complicated. So there's lots and lots going on here, and a lot of it is all interrelated. So I'm trying to sort of get across. Yes, it's hard, which is why I come back to it. You're going to have to do some testing yourself to get some real numbers, but we'll hopefully give you, as I say, some ideas. What about the impact on code complexity? Well, we'll try and show an example of that. And what about the impact of those constraints? So there's a lot going on. So I'm going to try and dig into a little bit of this to give you some initial numbers and an initial idea. So, as I said, lots of things to look at, not really independent. What I'm going to try and do, and I'm not going to be 100% successful, I think I'm going to be successful enough, is to focus on a single variable. What's the impact of using Loom on one particular thing? Now, keep in mind that performance tests are only ever going to be indicative. More so on here, because I have very carefully constructed these test cases to explore one particular option. They are not even close to a representative web application. So, again, it's just giving you an idea. And the other thing with performance tests is you're probably aware if you use Tomcat that it's got 3 variations of connectors, the NIO, NIO2, and APR native. One of the questions I often get asked is, which one's best for me? Well, that is, well, which one do you want to be best? Because they're all actually so similar. I can construct a test case that will show any one of them is the best. So you tell me what answer you want, and we can prove it. So again, keep in mind that, these things are all fairly close. And what we'll also see is the numbers are actually pretty small in absolute terms. So there's not actually that much in it, at least in what we've looked at so far. Java 21, of course, is still in early access. This was done with one of the very early builds of Java 21. I don't think anything substantive has changed, but you might see small differences if you rerun these tests with newer versions, and we might still see more changes between now and when Java 21 hits GA. So as I've said several times, this is just a starting point. There is a lot more to do from here. Some of it we can do generally at the container level. Some of it is going to be application specific. So let's try and look at throughput. So what I was trying to do here is I wanted to see, well, how much slower or faster is it to process a request on a virtual thread compared to a platform thread? Trying to remove as much of everything else as I possibly can. So I'm doing it with really small numbers, really low concurrency, because I don't want to get to the point where I have more threads than I have cores available, because I want to try and remove that aspect of the way the scheduler behaves. That's why the concurrency numbers are really low. I've got something else I can show you with higher concurrency in a minute. I'm not really interested in maximum throughput. I'm trying to look at what's the difference between, on a per request level, how much overhead does Loom add or remove from a single request? So it's the relative difference. It's 5 milliseconds faster, it's 2 milliseconds slower. What's that number, roughly? Now, because virtual threads do clever things around blocking and I/O, one of the things I thought, well, it might be that the size of the response is relevant, because that's going to require I/O. So if Loom is better or worse at I/O, then obviously with larger responses, we'll see a bigger difference. So that's why the response sizes are varied. I did a few things that you'd never do in production in order to, again, remove as much overhead as I could. And I wanted to try and make the two options the difference between them as obvious as possible. And the main thing I did is I turned off access logging. Now, that's not something I'd recommend at all in production. It's one of your key debugging tools. But here, access logging, because it's writing to disk, really slows things down. It's a significant overhead per request, much bigger than anything else Tomcat does in terms of overhead of handling a request. So I want to take that out, because then that will hopefully make the difference between virtual threads and platform threads easier to see. The details of the test environment and exactly what I did are all available on that blog. You're welcome to poke at that and point out all the things I've done wrong. And these are the results. So let's start at the bottom. This is the results for a 16 megabyte response. Hopefully you'll be able to see that one of these lines has got a little diamond on it. That's the virtual thread line. And one of the lines has got a little cross on it. That's the platform threads. And what we see there is for concurrency around 2 and 4, virtual threads are ever so slightly better. 8, 16 and onwards, there's not that much difference in it. So my takeaway at that point is, okay, I/O-wise, looks like virtual threads and platform threads are pretty much even Stevens. There's no particularly big difference there. So what happens as we reduce the amount of I/O, so we spend less time doing I/O and basically more time doing overhead, and that's where things start to get interesting. This gap, particularly 2 and 4 concurrent users, starts getting wider and wider as the response size goes down, and we're basically looking at more and more overhead. And you probably can't tell, but that really dirty, horrible line up here, that's actually the 3 smallest response sizes all overlaid each other in virtual threads, and the other dirty one is the platform threads version below it. Now, the thing that jumped out at me first was, hang on a minute, if I go from 1 platform thread to 2 platform threads, I get lower throughput? Hey, what? Huh? That doesn't sound right. What on earth is going on? But I did check it, and the results are correct. What's happening, and it's really sort of shown throughout of that, is that with platform threads, they're obviously coming out of the thread pool. The thread pool uses a linked blocking queue, and there is contention when you put a thread into the pool and when you take a thread out of the pool. And it's that contention that's creating the difference between platform threads and virtual threads. The virtual thread scheduler uses a work stealing queue that they pinched from the fork join pool by default. And because it's work stealing, it means that there's less contention. And that difference works out to about 50 microseconds per request. Now, quick poll, how many people here would be interested in saving 50 microseconds per request? How many people here is that significant? 1, 2, 3, a small number. Yeah, that's sort of what I'd expect. For a lot of web applications, that's down in the noise. For a few, it's important, but it comes with caveats, as we'll see in a second. Yes, the other thing that we'll come back to in a moment is you see here that once you get to more concurrent users than there were cores available on the machine, virtual threads start to do better again. That, again, is all around contention, and that's the area that I do want to look at in a rather more detail than I've had time to so far. But I do have some draft results for you. So if you start testing a configuration where concurrent requests are much, much greater than the processors or cores you have available, and credit to my colleague Violetta who helped with generating these results, then you do see something interesting. Now, the caveats, it's still a work in progress. I want to make sure it's repeatable. I'm not convinced I'm only seeing the result of this high concurrency. I think there might be other things going on as well, and I want to dig into that and try and work out what's going on there. And I'm also wondering, to what extent are these results impacted by the way the application behaves? So we're back into trying to isolate that one thing, and here it actually gets really difficult. And that's before you start worrying about, well, how's the virtual thread scheduler interacting with the OS scheduler, etc., etc. But what we're seeing fairly consistently is that if you switch to virtual threads, you do get higher throughput, but you also get a wider spread of latencies. And the reason for that is the way that the work stealing queue works. What it will do, it'll pull things out of the queue in almost FIFO order, but not quite. So those things that get pulled out ahead of time, they see lower latency. Yay for them. The ones that don't, they see slightly longer latency, so you start to see your latencies spread out. Now, if you're in the category of people that really care about 50 microseconds, you probably care about consistent latency as well. So this is definitely one of those where you really need to look at how does it behave for your application, because it's going to, it's going to be very application specific, so you need to look hard at the numbers. But make sure you look at it in the round, don't just concentrate on one figure. But yeah, certainly I want to do some more work on this. I want to try and get, like we've got that 50 microsecond number for the request processing number, I'd like to get some sort of numbers like this for this part of it, but there's a lot more going on. I think it's going to take a bit of time. So let's go and look at easy to use. Now, don't worry if you can't read this code. First of all, it means you won't see if I've made any mistakes. Secondly, it's not the detail of the code that's important, it's the volume of the code. So what I've got here, again, is another one of my artificial constructs. This is a really simple servlet that just counts the number of bytes in the request body and spits it out into the response. Now, if I write that in blocking I/O, it looks like that. If I do it in the Servlet asynchronous API, it looks like that. So it's about 2 to 3 times longer. Oh, and on top of that, I was biased towards the making non-blocking look better here. Non-blocking actually just swallows any errors that happen. At least with the blocking one, what would have happened is, okay, it just throws the error, but still the container would catch it, handle it, and you'd get the default error page. Here, it's just swallowed. So actually, we need a bit more code. And there were some shortcuts, some sort of simplifications I could do with the blocking code as well to make it even shorter. So it's probably more like 3 to 4 times more complicated. So you've got to write all of this extra code, and it's not just the applications that have to do this. Think about what's going on under the bonnet in Tomcat, under the bonnet in the Spring framework. There's a lot more plumbing to handle the asynchronous code than there is the blocking code. Error handling in particular is really gnarly. It's difficult to get right. And so what benefit could we get if we just said, oh, actually, we've got an application that's currently blocking. It's got scalability issues. Do we A, refactor it, or do we B, just switch to virtual threads? So what I've done here is I've run some tests with virtual threads on that blocking example and platform threads on the non-blocking code. Actually, it wasn't that example, it was a slightly different one. What I was trying to do was, well, okay, if I really want to test non-blocking, I need to have some sort of blocking service that's being called. Thing is, as soon as I introduced that, whatever delay I put on the blocking service, that dominated the numbers in terms of timings for the request. Even if I just put a 1 millisecond delay on it, it dominated. That was the dominating factor, and you couldn't tell the difference between them at all. So I ended up actually dropping the delay down to 0. So it is, again, another artificial test, but I think it does actually go through all of the overhead, which is the important thing, and compares the relative overhead of the two, and that's what's important for this particular test. And the results are, at low concurrency, virtual threads are better. Well, again, we kind of expect that from what we've learned on the throughput and the contention. And again, when the concurrency goes above the number of cores we've got, virtual threads look a bit better. But generally, they're pretty close. So depending on whether the latency impacts are acceptable for you or not, one of the options you've got, if you've got a web application that has potential scalability issues, that's using a lot of blocking API, switching to virtual threads could potentially solve that blocking problem for you. It could be a very quick win. Obviously, your mileage may vary, make sure you test it, but certainly it's the sort of thing you should be able to test quite quickly and a lot faster than you'll be able to test, well, I wonder what the benefits of refactoring it are going to be. Because you're certainly not going to be able to do that in an afternoon. Whereas switching to virtual threads, as of Tomcat releases that will be in June, is as simple as use virtual threads equals true on the connector. As long as you're running on Java 1 for Tomcat 11 and 10.1, that will just work. It's not there in 9 and 8.5 yet, but I've proposed it for backport and nobody's complained, so that's on the list of things to do next week. So it should be there in the June releases for all of them. So, some conclusions. If you're currently using non-blocking API, Servlet asynchronous API, reactive, other non-blocking frameworks are available, whichever one you happen to have chosen, you're unlikely to see much difference switching to virtual threads. You might see a little bit. I think it'll be a bit like the Tomcat connectors, to be honest. Some applications will be a little bit faster, some will be a little bit slower. It's try it and see whether does it make enough of a difference for you. Applications currently using blocking APIs, that's where I think you're going to see some big differences. Throughput differences, not so much. In terms of throughput numbers, how long it takes to process a single request, that's not really going to change that much. It's the scalability that's going to change. How many concurrent requests, how many concurrent connections that you can handle with that system. That's where I think the real benefit is going to be. Obviously, for that to happen, you're going to need to look at, have you got any long-lasting synchronized blocks, and how are you using thread locals. But there are tools available with the JVM to help you identify those hotspots. And for Tomcat, the synchronized blocks was a fairly easy fix. It's the thread locals that's going to take us a little bit of time. So, next steps. And I've whizzed through this rather faster than I was intending. Oh well. So, as mentioned, we'll have the virtual thread in the June releases. It's worth pointing out that the minimum Java versions required for Tomcat 8.5, 9, and 10.1, they're not going to change. Virtual threads will be available, but only if you run on Java 21. And we'll use our usual reflection tricks to make that happen. That, of course, is another question. How much overhead does that reflection add? Does that change the calculus at all? Probably not, is my guess, but it's yet another factor that needs to be taken into account. On the Tomcat development, as I say, we need to look at how we do this caching. We have thread locals. We have an internal thing in Tomcat called the synchronized stack, which is great for these sorts of caches as long as contention is low to not very much. And often, because the time to put something in and out of the stack is so small compared to the overall request processing time, actually contention on that is fairly low. So that might actually be an answer. We need to look at that versus new object. The challenge we have is based on some initial work I did last week, is that if you're running on platform threads, your best option is thread local. If you're running on virtual threads, your best option is new object. So given that we want to be nice to everybody, how do we actually square that circle? And I think what we're going to end up doing, and it's very much at well, I've had an idea and I need to go and try it and we'll see what happens, is effectively have adaptive caching. Right, if you're on a virtual thread, we'll do it this way. If you're on a platform thread, we'll do it that way. That will but that itself adds a little bit of overhead. So, yeah, it's a difficult one. Haven't quite figured out how I'm going to deal with that yet. I think that'll end up being a long discussion on the dev list. The other areas, obviously, we're making this available in June. People will hopefully start using it. I'm expecting people to find some bottlenecks, things that their particular applications trip over that our tests haven't. That will just go through the usual process. Report a bug. We'll take a look at it. With a reproducible test case would be nice, please. Makes our lives a lot easier. But we'll have a look at it. We'll address it, and then that fix will then be the next release. One of the things you're probably aware of is that Tomcat does monthly release cycles. And what we try and do, and we've been pretty good at it for the last few years, is we will aim to fix every open bug we know about in the next monthly release. So for the last few years, we haven't, when we've done the releases at the beginning of the month, we haven't had any open bugs that we know about, that we can reproduce, would be a slightly fairer response. There's a couple that tend to be open for a bit longer because we just can't reproduce them. But they do get fixed eventually, but again, it's all back to that reproducible test case. But yeah, the Tomcat code is generally pretty stable because we do that with the bugs. Okay, that I think brings me to the end of what I wanted to say.